Our next speaker on this connected stack is Dasith Wijesiriwardena. He's a lead consultant at Telstra Purple, and he'll be talking to us on the shell game called Eventual Consistency. Hey, welcome, Dasith.
Hello, can you hear me, Prashant?
Yes, I can hear you. I can see your screen.
Awesome.
Yep.
Cool.
Can you? Yep. So your
All right.
slides are
I'll
full
start
screen.
now.
Yes. Done.
Thank you.
Thank you.
So, good afternoon, or evening, or morning, wherever in the world you're joining this conference from. It's great to be talking remotely from the comfort of my own home. The talk title is the shell game called Eventual Consistency. So I want to do a quick tour around the concept, introduce this to folks who might not be familiar with it or new to distributed systems. It's 20 minutes, so I'll try to keep it kind of like overview. We don't have time to do a deep dive. My name's Dasith. I'm a lead consultant working for a company called Telstra Purple. I'm based in Melbourne, Victoria, Australia, and I've worked with many clients, enterprise clients, small clients, many teams of many sizes, and often I do build distributed systems, and I run into developers who don't have a lot of experience doing so, and I have a lot of lessons from the trenches and a lot of scars that I want to share about. So the aim of this talk isn't to do a deep dive, rather to show you some ways to deal with eventual consistency and arouse your interest. There's a lot of good material on the internet as to if you need a deep dive rather. So the agenda for today is to introduce you to this thing called the CAP theorem. I'm sure many people already know it, but for those who don't, I'll do a brief rundown of CAP theorem and why modern cloud scale or hyperscale systems prefer high availability over things like strong consistency, and how that yields us to eventual consistency. And we'll look at a few ways to deal with eventual consistency. And there's a lot of scope for creativity there. So I'll leave you with some ideas for you to take home and make your own. And then we'll do a recap. So CAP theorem. So the CAP in CAP theorem stands for strong consistency, or C, availability, and partition tolerance. The theory says that you can only pick 2 out of the 3 when developing a distributed system. Consistency means that you can write something to a node or partition, and that thing is instantly available. All the nodes become consistent with that particular change to the node. Availability means that even if something's disconnected, a partition or a node is disconnected, you can still access the other disconnected partition, but get stale data. It doesn't mean the system goes down. Partitioning means that even in a disconnected state, the partitions function as expected, and when the connectivity comes back up, they'll work as one system again. So this is a very brief rundown of the CAP theorem, but what I want to highlight is in a distributed system, whenever there's latency involved, so think of something in the cloud, the latency means there's a network partition. It's effectively a partition, so you don't really have a choice but to pick partition tolerance. So the real choices you now have are to do a AP system or a CP system. AP means available partition tolerance system. CP means consistent partition tolerance systems. So let's look at a couple of examples of each. In a CP system, this is what you build 90% of the time. The change propagates to all the nodes, but until it's propagated to every node, the system isn't available. So think of this as some kind of lock or transaction. So as a result, until everything's propagated, the system isn't available. And for cloud scale system, this isn't the most performant. And things get a bit worse when there's a network failure or intermittent connectivity between nodes as well. Because then until the network connectivity is resolved, the system as a whole becomes unavailable because there's no way to ensure consistency until that particular problem or network connectivity issue has been solved. So the reasons for building something like this is you really need strong consistency. So you need something like transactions to support invariant conditions that cover or span multiple nodes or partitions. And generally, it's easier to develop these systems because developers can fall back on things like transactions. Now, let's contrast that to an AP system or available partition tolerance system. So in this scenario, even if that particular update hadn't propagated to a node, the node's still available to be read or written. You'll get stale data, but that's okay. It will eventually have the most recent data. And as a result, it's really fast. We didn't require any sort of orchestration through transactions. So it's much faster than, let's say, a CP system. Similarly, when internet connectivity or network connectivity is lost, it's still okay. We can still have that node functioning with stale data. And once connectivity comes back up, it will be consistent as well. This is what we call eventual consistency. Nodes becoming consistent over time, but not immediately. So what does available partition tolerance system, what are the design choices? Is when high availability has priority over strong consistency. Stale data, we can deal with them in creative ways. But as a result, it becomes hard to enforce those invariant conditions we looked at before. So let's set the context in the modern landscape. So in modern cloud or hyperscale systems, availability takes priority, or it has a better seat than a strong consistency. We deal with things like NoSQL databases, and they don't really provide the same levels of strong consistency. To add to that, having distributed transactions covering partitions is very CPU expensive, slow due to network latencies. And if you're using something like CQRS or command query responsibility segregation, you have different read and write stores. So this is a reality. So you have to deal with eventual consistency. So having this reality of having to deal with it, what are the problems? The best way to show it is through another example. So let's take a CP system. This is a thing you built 90% of the time. You send a request to the server confirms it. It can confirm it because there's a transaction that covers all the partitions. And once it's confirmed, you actually, before confirming, the nice thing about CP systems is you can have these invariant condition checks. You can, all the partitions are consistent because the transaction covers them. And as a result, immediately after, you can look for the order and the order will be there. This is all good, but when there's millions of users doing this concurrently, transactions or distributed transactions rather don't scale very well. So as a result, you can have the system outages. And if you're not a technical person, it's very hard to understand this. And if users will not appreciate your system going down when they need it the most. So what if I told you there's another way of dealing with systems? But this means leaving the transaction safety rules you've been used to. This way involves the same request going, but instead of waiting for the change to propagate to all the nodes, we acknowledge it. I didn't confirm it yet, I just acknowledged it. And meanwhile, it's propagating to the other partitions. And once it's propagated, we'll have the order, but until we do so, if the user tries to look at the order, they'll get a 404 because the order hasn't been created yet in the other partitions. But eventually, maybe 300 milliseconds later, or maybe 3 hours later, they will propagate to the other partitions, and then the user can look at the order. You'll obviously see a problem here. The user experience here might not be great, and for invariant conditions, this might be bad, like the one where our order quantity needs to be less than available quantity. But it turns out it's not as bad as it first sounds. I'll tell you why. So Greg Young, who coined the term CQRS, he has some thoughts about eventual consistency. He says that if you have anything that goes over the wire, it's pretty much stale data anyway by the time you draw it on someone's screen. So embrace this reality. As long as you communicate using the right language and manage the expectation, you should be good. Gregor Hope, who's in the architecture team in AWS, he is a thought leader in this space, and he says that even real world, we don't really use transactions. In a coffee shop example, he says that the barista and the cashier don't have orchestration or orchestrated transactions. A barista has a queue he or she processes, and the cashier just keeps adding to the queue. So this disconnected nature allows Starbucks to have a high throughput of orders. So this is similar to eventual consistency in that the queue acts as a means of making the barista eventually consistent. Udi Dahan, who's another industry leader and creator of in-service bus, he says that invariant conditions don't really exist in the real world. What we think of invariant conditions are really naive software development rules. A good example is that quantity available and quantity in the warehouse. In the real world, the software system saying we have X number of quantity doesn't mean the real physical warehouse is going to have that quantity. So rather than trying to naively enforce that, think of the domain, understand the business more, I guess, deeply, so we know there are compensating actions when something like that happens. So with these industry voices putting their weight around asynchronous business processes and eventual consistency, I think it's okay to think of this favorably. But what does this mean for the user? We said we want to manage user expectations. The last thing we want is a pissed off user. So with eventual consistency, it's important that we be honest with the customers. Don't confirm anything unless you know with a certain amount of confidence that you can fulfill an order. Instead of saying things like order confirmed, say, oh, order is queued, or you will confirm it soon. Use multiple mediums of communication. I can't stress this enough. Let them know, and let them know fast. Email, text, you can't over-communicate. And understand that compensating actions are a must. So learn about your business, how they operated maybe before they had software systems, how they compensated for certain things. Think of a order as a long-running business process that ends with compensation when something goes wrong. So I'll also show you some ways to deal with this in the UI. And these are not all the ways, but some of the ways you can mix and match some of these things in the UI. So I'll talk about disabling and long polling, using a thank you screen, and faking in certain situations when some things are critical or consequential. You can actually fake the data to show the user as if everything's okay until the backend has a heartbeat to catch up. And finally, WebSockets or HTTP2 to have asynchronous callbacks to tell the user the actual state everything is in. I'll show you a few examples here because it's easy to understand. In this example, we make the order, we get an acknowledgement with the order number back. And as soon as we get the acknowledgement, we disable the UI. And meanwhile, the backend is propagating that change to all the nodes. While it's doing it, we are hitting the server every X number of seconds, seeing whether the order is being created. And if the order hasn't been created, we still keep it disabled. But after a while, when things propagate and the order is confirmed, we redirect the user to the order details page. Very simple. I've done this on many projects. It works. But the downside here is long polling can really take up server resources. So if you have millions of users, this might not scale very well. On the flip side, you can use a thank you screen. So the same thing, you get a order acknowledgement back. This time, we show a thank you screen while the backend is syncing. Now, the idea here is the thank you screen, there's enough information there to keep the user occupied until the backend has had a chance to propagate the change. And by the time user clicks the order details button, voila, we can show the details of the order. But you may have already noticed a problem with this approach is what if the user clicks on the order details before everything goes okay? So, yeah, that's a reality. You can combine this with long polling or some of the latter approaches I'll discuss today. But this is a technique that many systems use. For example, your movie ticket order might already be doing this. The other way of dealing with this is to fake it. Now, I don't recommend doing this for consequential or critical things like ordering a $3,000 TV. Don't show them a fake order. Do it, but adding a comment to a thread, perfectly okay. The user experience is still the same, so you get a comment ID back acknowledging that the request was received. And this time, we add that particular comment to local storage or session storage in the browser. And I'll show you how this becomes handy. So after adding it to the local storage, we render that comment right at the bottom of all the other comments. For the user, it looks like it's gone ahead and confirmed it. But if the user refreshes the page or goes back to another one and comes back, you'll see that the response from the server will not have the comment in the response body. But that's not a problem because we have the local storage. We have our previous comment saved there. And what we're going to do is merge the comments from the server with the comments saved locally and give it to the view to render. And it looks like it's the comments there coming from the server. But because this is a local storage, only that particular user will see their comment. The other users won't see that yet. But eventually, things become consistent, the nodes become consistent, and all the users can see it. Now, things like Facebook use this very well. They will have different propagating ratios or different things like your country or your city might see your comment first, but the rest of the world later. So these are very interesting ways of dealing with real life problems. But the best way I've found is to be honest with the user and show them a status. So when you get the order ID back, we simply have a notification showing you can put a spinner. It doesn't have to indicate the on-time status on the server. But when things are confirmed, we give them an alert, a notification saying that things are ready. And upon clicking on the order, you can show them the order details. Now, this scales rather well, and it works for many scenarios. And this is my go-to choice if I have the time. And my user interface has already got a concept of notifications. So all of my examples, they looked at things when everything went well. But partitions, when disconnected, can have conflicts. So your order, there's a chance it might not get confirmed. How do we deal with it? So it's important exception conditions are dealt with immediately, and you show the user on the details on screen if possible. So over communicate, please do. It might be a text message, might be email, like I said before. The faster you do it, the better the users will appreciate it. Compensate the customer. You have a plan. Even your level 1 support needs to know what to do when a thing like this happens. When a customer rings back with the order number saying, where's my order? Better way, don't charge the credit card until you ship it, so you don't even have to do a refund. So think about long-running business processes. Don't naively think anything in the real world is synchronous. This is a summary of the things I spoke about. I know I went through it very fast. The aim is to just spark your interest. So disable long polling is easy to implement. The UI isn't great because UX isn't great because you have to make the screen unresponsive. A thank you screen a bit better, but it assumes that assumes about the user taking a bit of time to read it. You can combine the two. Fake cache, again, very creative way of dealing with it. But for non-consequential scenarios, live progress, I think it ticks all the boxes as long as your front end allows for a concept of notifications. But yeah, it uses WebSockets, so your server needs to support that, or backend application rather. So embrace the real world. 90% of what you're going to build, I'm going to tell you now, is going to be a CP or system, a strong, consistent, partition tolerant system, but that's okay. Even then, the tricks you learned today about dealing with eventual consistency, you can still apply to those things. The rest of the 10%, where you're building a highly available system, definitely think about the tricks I told you, even when building something like CQRS, a CQRS system or a messaging system. In all those use cases, the idea is embracing long-running asynchronous processes. Don't assume anything is synchronous, not anymore in the real world anyway. To wrap everything up, I've got this awesome comic that explains eventual consistency better than I ever can. Just Google eventual consistency comic because the text is very small. But I'm happy to take any questions if you have any at this point.
Yeah, thanks, Dasith. Yeah, there is a question from the audience. So, have you ever encountered when the system fails? How do you handle a possible data loss because the information hasn't been received by the server side?
Right. So this is one of the failure conditions I spoke about. So there's many reasons why you might have a data loss. It might be because two partitions are disconnected for a time being, and their worldview forks from one another, and the majority needs to win. That's one scenario where data loss can happen. But I've dealt with scenarios more so with NoSQL databases that this thing happens. And when it happens, you have to have tracing, logging, and when a plan to have compensate if there's an end user involved. So there's no easy answer. It depends on the business context. But this is where your tracing, logging, and everything comes into play. If you have a correlation ID to wrap everything together, perfect. That your support team can use that.
Great, Dasith. So I have a question. So we all, so your session was mainly focused on, say, examples were on the e-commerce side. So we all use e-commerce site day in, day out. So from that perspective, how much percentage of the websites do you think do understand and handle the things that you are highlighting?
Right. I think most of the systems are eventually consistent. So take Amazon, for example, right? You go in and you create an order. Don't think that the order is propagated through their systems when you see a order acknowledgement in the screen. That's why you get an order email a few minutes after. And
Okay.
they are pioneers in this. And that's why they can scale their systems to millions of users. Now, Google, on the other hand, they've got a database called Spanner. I think the open source version of that is called CockroachDB, which aims to be strongly consistent, but as performant as available AP system. So different technology giants are doing different variants of this, but I think you still need to understand asynchronous processes and how to deal with them in your UI.
Okay, great. Thanks a lot. I'm sure the audience liked the session. They could really,
Thank
I'm
you.
sure they could really relate to the energy that you had, the
Cool. Yeah, hit me up on Twitter or on chat. I'm happy to answer any questions after. Thank you.
Sure. Thank you.